Okay, let's keep going. So we want to review what's autonomous end-to-end autonomous driving happened in the past, current, and onwards. Uh, this is our schedule today. First, we will go over introduction of end-to-end autonomous driving, and we will list out the roadmap of its happening. And then we will introduce our recent work about end-to-end, we will say 2.0. It is a work engine to solve corner cases, emerging corner cases in many industrial and academic research. And how does that work engine means? It is actually I would say a work model, but with a closed loop reconstruction scenario, so that I would say a driving agent could roll out in this simulated world and have a better ability to solve the corner cases. And still, during our development of such a work engine, we will face many key challenges. For example, how to scale your RL agent during such a rollout manner. And it is quite interesting. I will introduce this later. So first thing first, what do we mean by autonomous driving? It is actually learning a single model that map raw sensory input directly to driving decision. Here, driving decision, we actually means acceleration, deceleration, steering of how our human drivers will do when you drive the car. And this is to replace many traditional module pipeline with, I would say, a unified function F. So such a F will map the observation plus the goal to the control signal of the vehicle. So the observation mainly cover images, point clouds, and vehicle status, while this could be mapped to another term in robotics, which is called the proprioception. So with this observation, we want to directly generate the control of the vehicle, which is the steering, brake, and throttle. So this is the main setting. So how do we train such an agent? It has two trending methods to do this. One is what we call supervised learning or imitation learning. The other way is using the reinforcement learning, which is a trend in the past like 5 years or 6 years. But for now, many end-to-end driving people are directly using imitation learning instead. So here is the main roadmap of end-to-end driving works start from history. So actually, end-to-end driving is not a very novel term when we talk about today. It actually emerged from 1988, where we have a very simple convolutional neural network end-to-end driving agent using imitation learning to try to drive the Jeep car. There's a very old challenge held by CMU to try to solve this task. And then come to 2020 and 2021, as we have a very good simulation called CALAR and many researchers along this way to do end-to-end driving research on the CALAR simulator. And after all this year, 2022, we have a very great work from the University of Tübingen by Kasia Chita. It is the NEAT, where we actually incorporating transformer architecture to end-to-end driving model, which likely boost the performance a lot compared to traditional convolutional neural network architecture. And then the end-to-end driving, autonomous driving term actually hit the people when UNAD win the CVPR best paper in 2023. So actually at that moment, not only the academic, also the industrial side of people have interest in how end-to-end autonomous driving might work in many cases. And from 2024, there are actually two lineup of research in end-to-end autonomous driving, which we call foundation model impact. So one kind of foundation model we talk about today is what we say is word model or video generation model, where you wish the generating filter of the current state will guide you drive through the corner cases or complex scenario. And another line of work is utilizing language model, or we prefer vision language model, where you wish you use the common knowledge learned from web scale data, and that kind of common knowledge is installed in the vision language action model. And you wish such kind of common knowledge will help you solve the endless corner cases you face in everyday driving. So these are two kind of trending technology today with vast improvement in the foundation model, and I will call a very quick application in the driving side. But will this? But here I want to raise a question to everyone here and to our group as well. So will we truly believe that foundation model will help us solve any corner cases in autonomous driving? If so, what kind of corner cases is it actually solving compared to previously traditional method? So seems like autonomous driving research are for now and for industrial side are really focused on how do you handle endless corner cases when you collect data in everyday driving data. So now we want to slightly shift our focus on how to solve it to how to create it, because we are vision people. We first our I would say secret method to solve every problem is that you collect enough data and you wish learning from data could help you solve the problem better. So based on this assumption, we actually shift our attention to how to create corner cases in a traditional driving model development pipeline. So this is a very, I would say, easy pipeline of how a general driving agent is created through data collection pipeline, training pipeline, and evaluation pipeline. So like many autonomous driving companies right now, they are collecting data using either their data collecting vehicle or their customer vehicle like Tesla. And when they collect the data, they when they face such kind of failure, such as sharp braking or collision with other agents like human or other vehicle, they collect such data and they put back into their data pool for retraining their driving model. And when they finish the training, they put the well-trained model back into the evaluation cases where the evaluation might be performed by the other data collection vehicle car. And then if you face a new bad cases and you just re-go again the loop to the how to handle the bad cases and again and again and again. This kind of things happening since like 2022 for Tesla and many other electronic vehicle companies. And we see that after 3 years from now, people seems not to have autonomous driving everywhere for their car. So it must have a problem in this such a timeline that you couldn't collect corner cases day by day, month by month, even year by year to try to solve the what we say the level 4 autonomous driving. So we here want to raise the question that can we collect all the corner cases without going such a loop? I mean, without going such a real world deployment that you really collected your corner cases from your everyday driving. So so before how we solve this problem, we also want to say that such kind of corner cases is really rare in many autonomous driving companies daily data collection things. So here is a figure of a Tesla FSD in the city. It is a graph showing the distance of critical disengagement, or in another term, miles per interaction, to show that okay, Tesla is actually reaching better and better planning performance. Like previously, they have only less than 50 miles for you to interrupt. For now, you could have 237 miles for you to interrupt. That means that average every 233 miles, do you need to intervene your self-driving car. So you see that if this miles goes up and up, it might have the probability to cover your daily driving because normal people didn't drive 200 miles. Normal people didn't drive 200 miles in your like a single drive or so. So, but even that, we could see that it is very hard. It's even harder and harder for company like Tesla to collect it, so-called bad cases or corner cases. So here we introduce a dilemma here. One is that valuable corner cases become increasingly rare because you seldomly face a corner cases when you collect your data in your daily drive. And on the other side, collecting such a corner cases on dangerous driving can actually risk your lives because this is how a human driver interact with the world with your self-driving car. It is not in simulation. It is not in very safe in a very safe setting, such as manipulation in robotics, navigation of your cleaning robotics in your household. This is actually driving on the road. So we don't want to be a very risky driver on the road to collect such rare corner cases. And this is actually raised by Harry Xu and Harry Liu and Shuofeng in a Nature Communication paper, what we call a curse of rarity in autonomous driving vehicle. He actually reprint the left figure here, saying that when you have less and less corner cases, the expense of collecting corner cases is actually raising and raising again. So we might, at the point of here, saying that we want to collect like a reasonable corner cases, reasonable amount of corner cases with reasonable considerable expense at your development process. So this is still the figure from the previously daily employment of your model, but we want to focus on the planner and the work engine side. Like, could we generate the valuable corner cases in simulation only? This is also the main motivation of many simulator work in current day. So for example, in driving we have car simulator, new plan simulator. In robotics they are much more like Mujoko, Isaac series, and previously Genesis. People want to solve problem in simulation and don't have too much effort in your like real deployment of your work. So what's the problem with simulation right now? The problem of simulation of color is its simulated scenario is far from the real world. So when you train your model in color or any kind of simulator, it will face a sim to real gap when you deploy your model to the real world. So we want to solve this problem fundamentally. Like, we actually simulate the scenario from the real world data, not from the graphics technology in the color or any kind of in any kind of this I would say not so fake, but this has a really big gap. There's a really big gap between the simulated graphics and the real world graphics. So this is how we want to solve this problem in a whole. So we first want to have the risky initial condition where we think that corner cases or bad cases might have a big chance to happen. So this kind of condition can be either collected in like many source scenario, where we say raw data collected by daily driving, because in daily driving, you will face many cases like you happen to collide with any other agent, but you have a sharp breakdown so that you avoid such a collision. And by collecting this risky initial condition, we have a behavior board model to actually simulate the collision or to other agent or out of the row or any kind of bad cases you can imagine with the world model. And based on the world model, we actually simulate or reconstruct the real work using Gaussian splatting or nerve style technology, so that the sensor input of these corner cases is actually rebuilt for the end-to-end planner to train the end-to-end planner. And then this kind of closed loop corner cases reconstruction is could be well done in the simulation only way without risking drivers' life in daily life to actually collect the corner cases by themselves. So we could now try to do this in a simulated manner. So then I would like to expand into detail how we actually ensure that our simulation is close to real world. By what do I mean by close to real world? It means actually the sensor input scenarios is close to real world. The distribution of the world status is close to real distribution. And this is actually going to happen in many daily driving, but not collected by autonomous driving company. So first thing is about how we generate a scenario based on what we say here, the risky initial condition. It is what we call a behavior world model. So we will introduce Nexus. So how we decouple the diffusion sparks adaptive scenario generation. So the task here is to give a map information and the historic full scenario agent status, and to output the future agent status, such as waypoint, velocity, and dimension. So before we go into this topic, I'd like to tell you why this is so important in auto-driving fields. Because as you know, people driving follow many kind of traffic rules. Like you need to obey the traffic lights, you need to drive in your own lane, and many rules are already told when you get your driving license. And this is how actually auto-driving people creating data. They also want to create such agent that, okay, you follow the general common sense traffic rules, but sometimes you're going to take some risky driving behavior, such as changing line, maybe or maybe not rushing for red traffic lights also. So we don't want our agent to drive reckless. I mean, reckless is like driving likely to nowhere on the road. It still perform some kinds of common driving behavior, but at some other point, they take risky behavior. So following this motivation, we want to ingest such kind of knowledge when we simulate the agent's behavior. And simulating behavior in a future status is generally called a world model. But for now, we don't take the actual world, but we see the all the agent in the scenario as a world state. So here is a visualization of what I talked about to give you a better sense of what actually we are doing. Here on the figure, you can see that there's first, it is the many lanes and traffic road on the map, and then the red curve and the blue curve here actually showing how the agents are moving around based on the initial condition. And I want to tell you that all this vehicle moving around is all controlled by one model, what we call the world model. So that the world model is responsible to simulating all agents future stated. So this is you could interpret like this is actually how the world is going to happen in the future. So based on many possibilities. And here it is actually how we simulate what we call the corner cases. And in the left figure here, it's likely to have a collision when the two vehicles are moving onwards. And on the middle, it's likely to have a cut-in collision when you have a left vehicle cutting in your own lane. And if you do not lower your speed, and it's going to be a collision again. And it's on the right side, it's actually happening a collision. You see that the two vehicles are driving on the opposite direction, and collision happened when their bounding boxes overlap at a very considerable range. So let's go deeper into how to develop such a world model. As I assume that you get the core idea of it. So the key challenges here is to balance the reactivity and control. So this is two terms that might not be too familiar with you in the world model setting. I will go this one by one. So actually, what do we mean by the sorry, I couldn't change the slide. It's actually we call the reactivity and the goal orientation. So what do we mean by goal orientation? Because although we don't know how the world simulated, we still want what is the final status of the world when we created corner cases. So here, the goal is actually that we want collision. We want the ego vehicle or other vehicle driving out of the road, like going to grassland or going to the river, any kind of it. So we actually have a definite goal state where we want to trip, but we don't know how to go to the goal state given our initial conditions. So this is one kind of feature we really want our world model to behave like. Okay, I don't care how you evolve in the future, but at the final state, you will go into a collision or you will go into a bad cases. So, so how to achieve this? There are many diffusion-like methods to achieve very good goal stated through like what we call a fully sequential denoising. But the problem is, although this denoising or diffusion-based problem could help us achieve goal in a very good manner, but it cannot react to dynamic environment changes. So what do I mean by react to dynamic changes? Means that, okay, if you happen really bad things during your imagination process to the goal state, it might turns out that, okay, your vehicle goes from like 0 kilometers per hour suddenly up to like 100 kilometers of hour, and then suddenly go back to 50 kilometers of an hour. So this kind of sudden changes, it doesn't follow the physical real world common sense, but it is possible when you diffuse when you diffuse a scenario, because such kind of knowledge is not injected into them. They don't know, or say the world model doesn't know how the normal behavior driving vehicle will done in a like a real world setting. And however, we could have very good interaction with the other agent or follow the what we say physical driving limitation for the next token prediction, and I would say autoregressive manner. But these are really reactive to changes, but they can easily lose the track of the long-term goal. Say, okay, we do have a very good next token prediction or next sequence prediction of the agent, while during the interaction of the real world, it comes from opposite side of the goal state. So this will violate our goal to like our motivation of constructing this world model is to achieve a goal state while it's going to another state. This is not what we wanted. So the key challenge is here to balance these kind of key features that we wanted for the world model. So so here's some insight of how we're gonna make it easier to achieve this goal. So actually, diffusion process. I'm not sure how many of you know how diffusion model works. So I'm gonna give a small thinking here. So diffusion model actually is trying to diffuse from noise to achieve any kind of goal stated you like. So this kind of goal stated would be like word stated, image view or video view, which is more developed in the AIGC field. So during this kind of diffusion process, we assign different level of noise per token. So during this kind of diffusion or denoising process, what we say the low noise token might be easily to be diffused when it has a very low noise added to them. While the high noise token are very hard to diffuse when we add a very high level noise to its token that it is very far from the real world distribution. So we try to say that low noise token is able to the control or goal orientation, while the high noise token is responsible for the reactivity of a different kind of agent. So here are at below there are three kind of figures that it is not sayingly what happened for diffusion model, but it gives you like a very good illustration of how the diffusion model is going to work. So on the left side, like you can see that those points are coming out of nowhere or coming out of everywhere to form a final goal stated. So it is very easily to be done, like state-of-the-art diffusion model, but you couldn't control how it's gonna form the curve. But you finally have a curve. That is what we say a goal stated. And on the middle side, it is actually, you can see that a line going from its initial point. So it is called what we say the autoregressive manner to do it. And you can see that, okay, it could go a very smooth or very good curve, but at the final goal state or a final endpoint, it could not be what we wanted. So so our method is on the right side where we call Nexus. We incorporate low noises token and high noises token all together, so that you can see that the noise token are actually coming from the initial state, but the low noise token are reaching to the goal state, where goal state we use a small red star here to red astro here to this state. It could reach the goal state very soon after a few steps of diffusing, while the other high noise token are trying to model the reactivity between different agents to form the curve, actually the curve here, to say that, okay, you have a reasonable curve, reasonable reactivity between different agents when you simulate to the goal state. So our method here is want to build these things up with bridge the gap between the reactivity and control here to reacting to real-time changes while following the predefined goals. And here is a figure of, I'll say, pipeline of the method. I'm not going to go into detail, but I will say the high-level takeaway is that we assign two kinds of noise to the token to help us balance the goal orientation and the reactivity. All these things are done through the backpropagation. I would say honestly, we don't know what happened during the diffusion process, but we reach what we want the feature, we reach we want the feature during this kind of design through a noise level control. And here is how we actually see the diffusion token involved during the schedule. The first one is the regressive one. Okay, it generates future states step by step. And the second left one is what we say the fully sequential denoising part. Okay, it's still going to generate step by step, but at the final part, the feature is gonna be diminished after too many steps of diffusing. And here we want to reach a balance between them. So we have the pyramidal scheduling, where we maintain the autoregressive involving while we have the fully sequential scheduling to perform the feature diminishing. And then finally, the trapezoidal, the scheduling is even harder for them to achieve by we sampling the tokens universal from left to right. And here is how we evaluate such a world model. So a key question of you might be, how do we actually evaluate such a world model? So actually, we still evaluate them like a motion prediction task. Like if we want to see that the simulated future of the state is actually what we want. For example, we want them to collision, and if the final state comes to a collision, but before our determine the final collision, it wouldn't happen any collision before the collision. So we think that this is a good sample of the model. So we actually want the behavior world model to react to the work like what we think. Like this is how we put that in a matrix to I would say quantitatively study the quality of the generated future. So general metrics here is the ADE, so the distance arrow between the ground truth trajectory and your simulated trajectory, and some collision rate before the corner cases or back cases happen. And here is again is the visualization of it. We actually I would say master the world involving in a very good manner, so that it follows common driving knowledge, while it will have final bad cases happen after our controlling of all the agents in the scenario. And okay, as you see here, we are actually simulating the world in a rasterized representation where we have road maps and we have vehicle like mounting boxes, put it on the visualization. But this is actually not end-to-end driving vehicle perform. End-to-end driving vehicle actually based on the sensor input to make decision. So the next question will be, how do we transform such a rasterized representation to a real-world observation? Real-world observation looks like this. You have image, you have LiDAR, you have all kinds of sensory to observe the world. And the abstraction of such a work is the rasterized representation we see before. So now the question is like a bit worse. Okay, we actually know the worst data already. How do we revert it back to the real world? So this is a kind of main things we have kind of a main work done by the graphics people. It is called the reconstruction, 3D reconstruction of the real world. So we utilize this kind of technique, but we found that there are some unique technology which is suitable for driving people here. So it is called the multi-traversal Gaussian splatting. So the motivation of it, I already say that we want to reconstruct the world from the single traversal, from the rasterized representation of the world. So first corner cases are, oh no, sorry, no corner cases. First challenge here is that reconstruction from a single traversal is very limited, I would say. So here you can see that the left figure here is the original view. And if we want to do a lane shift, like 1.5 meter, you can see that there's a very big distortion on the view on the sky here. And then if you shift the lane even further, 3 meters, 6 meters, you can see that the lane is not even visible. The vehicle is got blurred in a very bad manner. And then this kind of image is actually not in the training set of the driving, in the end-to-end driving model. So we want this kind of figure here to be really photorealistic, and it is able to be trained by the driving model. So there is no such a sim to real gap. So our motivation here is say that, okay, this kind of reconstruction, they only based on single traversal. That means that, okay, you only traverse this kind of scenario one time, and then you want to reconstruct the whole world by this one-time traversal. We think this is limited, and this is not going to be happen as we are vision people. We based on the belief that more data will give you better performance. So we wonder, where is the more data in here comes from? Actually, it comes from multi-traversal. Like during your daily life driving, you didn't traverse your neighborhood, your block, your community one time. You go from the left side to the right side on your way to go to work, and you go the right side of the left side when you get back to home. So actually, you will have multi-traversal in the scenario, but not only one traversal. So multi-traversal data from daily commute will give you a very effective view interpolation across line. Say that, okay, you might go the left lane in the morning and the right lane in the afternoon. So everything between right lane and left lane, you have already seen in your whole day. So reconstructing the whole scenario from two observations is absolutely better than, okay, you only see the scenario one time during one traversal in the scenario. So also you know that this might be very challenges for reconstructing the world, because you will argue that, okay, the lighting condition, the vehicle distribution is totally different in the morning and in the afternoon. So these are actually the challenges here. So we have various appearance light, and we have a transient dynamics in here. And this is actually the key challenges when you want to do reconstruction, because I would say ordinary reconstruction work actually assume the work is static and everything remains unchanged, so that you can reconstruct such an unchanged or static work by one traversal. However, in here we have multi-traversal and dynamics here. So how to tackle this kind of challenge is I would say a unique question faced by the driving community. So first thing first, I still want to give you the visualization of the task itself so that you could get a better sense of work, better sense of the task. So on the left side, we have a traversal number one, like we going on the right lane. The right lane is that right to the yellow line here. And then we want to move our vehicle, like move our vehicle to 1 meters left, 4 meters left, and even 8 meters left. Here we are actually putting our ego vehicle on the left lane already. And you can see that the consistency remains pretty well after such a movement. And also this is going to happen when you do on the left lane here. And here the left lane is actually the right lane on the figure number one. Okay, in figure number three, we are on the left lane now, and we want to shift our ego vehicle to the right lane, so that you could see that the consistency still perform very well. And I'm going to show you how this is going to work if you are a Gaussian splatting or reconstruction guy and you wonder how we remain such a consistency. So actually our workflow is pretty, I would say, straightforward. Okay, so if we have too many dynamics vehicle dynamics light conditioning in the scenario, we decouple them. We decouple all the vehicle into single noded, and we decouple lightning condition as another single node. And then we form a scenario graph based on this node. And then every time we simulate the world, we select what kind of I would say the actual node that could have effect to our reconstruction, and we reselect them and we render them in the scenario. So this is very straightforward. It has I would say a very intuitive way to tackle this problem, but I will go into detail how we gonna reconstruct the node, how we gonna deal with the lightning condition, and how we gonna re-render the vehicle in the scenario again. So first thing first, so based on the multi-traversal data, we obviously have different vehicle placing in different position when you have the data. So the first task is to detect them. So we want to detect all the vehicle, all the movable object in the scenario, and then we just added them out of the scenario. And this will gonna give us a bunch of the vehicle in the real world. And here you could say that on the figure above, you have a vehicle on the road lane. And then on the below figure, we render them in different position with the same vehicle. So this kind of the moving object detection and retrieval is done in the first step here. And then we want to add some learnable threshold for them for the residual for each kind of Gaussian. So actually here, each kind of vehicle is represented by a Gaussian core here. And then we move the transient nodes. We'll put the car on the ground, and then this is how you look in the right side here. We re-render the object in the scenario. And such kind of rendering actually follows the physical rules. Like we actually do the depth estimation, the semantic depth segmentation, and you see that it is actually following the physical world, so that even a detection method or a depth method could not tell the difference between the simulated images and the original images. So which means that our simulated images quality is quite good. And then second step is that we want to align exposure across multi-views with the LiDAR anchor. So we know that RGB might reflect the lightning condition when you have low light, we have highlight, everything, but LiDAR is consistent. So no matter what the lightning condition change, the LiDAR sensory result is consistent across different lightning conditions. So based on that assumption, we put the LiDAR as an anchor and re-render the image or the RGB images with the LiDAR anchoring the position of the object, so that the lightning condition could be smoothed by the LiDAR prior here. And then through all these kind of super detailed techniques, MTGS outperform all the SOTAs on the multi-traversals reconstruction phase, and we actually improved the performance a lot. making the reconstruction results, I would say, applicable to train the end-to-end driving agents. And here is our result of the reconstruction. I want to tell you that the train number 1 and train number 2 is in our data, and the train number and the unseen at the below is actually our rendering result. You will see that we remove all the vehicle on the roadside, and still the lane and the road and the background object remains very consistent during the rendering of the process. And here we want to show that, okay, now we already have Nexus to model the world behavior through the world model, and the MTGS to render the scenario. Now we actually can generate what we call corner cases. So here is what we show you the corner cases looks like. Okay, collision, and collision again. So this kind of collision data could be generated at a batch to have your driving world model be aware of what conditions might happen from a data perspective. And based on all this kind of technique, we hold a challenge called the Nexus V2, pseudo-simulation for autonomous driving. We actually put these corner cases in the test batch to see that, okay, if your driving model to handle collision pretty well compared to the baseline. And this is done with the in a collaboration with the University of Tübingen, NVIDIA, Bosch, and many our industrial friends here. So before we go into details about this, so how do we actually evaluate if the driving agent is good enough? There are kind of two things to do that. One is what we call the open loop evaluation. So what do we mean by open loop is that we actually log the human driver behavior in when a human driver drives his car across many traffics. We memorize such kind of human driving trajectories down to the log data as a log data, and we train our model upon on the data, and we want the model actually to mimic how human driver will do. Like in a here is a stop sign intersection. If the human driver comes to a stop, and the end-to-end planner also need to comes to a stop, but it is nowhere for the end-to-end agent to know why it comes to a stop, because the human driver know that there's a stop sign here, but not the end-to-end driver. It is actually learned from in a data-driven way. So this is kind of called the open loop evaluation, so that the trajectory is fixed, and all the driving agent needs to do is to mimic the trajectory itself. It is not evaluated by traffic rule, not evaluated by like maybe police, LAPD, whatsoever. So this is kind of open loop. It doesn't model the compounding error. It also doesn't model the causal confusions. Compounding error means that although you might mistake at the very beginning of your driving behavior, but still the log trajectory will drag you back to the correct path after your mistake happened. And also, it doesn't model the causal confusion. For example, like if you have a very sharp brake, the vehicle behind you might also come to a brake as well. But in the open loop evaluation, it won't. It just go crash you without any reaction to your behavior or to the end-to-end driving behavior, end-to-end driving agent's behavior. So in that way, we want to propose what we call the closed loop evaluation. So we model the compounding error and we model the causal confusion in the scenario. And how this is done? This is done by the Nexus and MTGS I mentioned before, to have the closed loop reaction to the world state is changing. So even if it is on synthetic data, we could have a very compute intensive things here. So first thing is to require to sequentially render the scenario as you see in the MTGS work like this. It need to require sequential rendering and require sequential modeling the inference. So this might put a very big compute burden on when you do one-time simulation. So So what our solution is, like, we do a pseudo simulation, not a real simulation. Like, we believe there's a strong belief here that, okay, even driving model could drive anywhere, but we believe that there are such many kind of, I would say, fixed pattern how you drive in the future. Like, for example, now you are at the stop sign intersection here. All you can do is either you go straight ahead, turn left, and turn right. You don't want to turn to building. You don't want to turn to the vehicle on the roadside. So in some cases, your future is somehow fixed based on the common driving rules or the physical limitation. It is not going to happen anywhere. So based on this assumption, we could lower down our rendering effect, our inference effect to a very low level. So here the rendering actually is split into two parts: stage 1 and stage 2. In stage 1, we render the scenario in a real world observation based on the planning result. And in the second stage, we use the pre-generated synthetic observation based on your planning results. And then we have a combined scope here to how to evaluate your driving behavior. Here is that if you align to one of our generated results, you are having a very good driving behavior and you reward here. But if you have if you distracted from our generated result, and you will probably get a low score because this kind of distraction might lead you to uncommon, or we say truly risky driving behavior in the real world setting. And then we so that with the compute efficiency, we have the pre-generated sensor rendering, and so that we allow a parallel model inference here, so that based on the same initial condition, we actually generate several possible future, and we evaluate the several possible future at the same time. So this is if you are an RL researcher, reinforcement learning researcher, this will give you a sense that, okay, can we do rollout here? Can we roll out the all scenario based on all the possibility here, so that the ego vehicle could actually learn how to drive in any conditions? And the answer is yes. We want to wonder how many IL training iterations are needed for the robotics end-to-end driving, because as of now, we have the possibility to roll out one scenario, and we wonder that how many iterations for RL algorithm needed to actually master the scenario. And there's a paper from the Apple Robust Autonomy Emerged from Self-Play on ICML 2025. It actually raised and tried to solve this problem, but it solved it in a very, very brute force ways. So what did this paper tell us? This paper tells us that you need 1.6 billion kilometer to train your RL well master scenario. So what do we mean by 1.6 billion kilometers? It's actually going from the sun to the Saturn. So it is actually not a plausible way to train in the real world. So you couldn't collect such kind of data to help your driving agent actually master the scenario. So but the result is quite good, because they tell you that after 1.6 billion kilometer training, it actually could give you a still shot of real world data set with nearly zero collision. So this is actually amazing. This could give us some hope that, okay, if we can find a way to lower this 1.6 billion kilometers down, we could also achieve a near zero collision based on what we found previously. And okay, there's even how they do this with the 1.6 billion kilometers to near zero collision story. It has many strong assumptions here. So first one is that it assumes perfect perception, so that you are not going to lose any kind of object, vehicle, pedestrian, cyclist on the scenario. You're going to detect them all by once and all perfect. So, and then second one is that it is work on a very simplified scenario representation. Okay, in such a scenario, you don't have traffic light, you don't have all these distracting distracting traffic sign on the road that will tell you to do slow speed, beware of the pedestrian crossing, all these kind of things. And it needs too many samples. So we want to raise a question that do we really need this 1.6 billion kilometers for end-to-end policy? We want to say that, okay, it might not be the cases. So based on our previous work on how to generate corner cases, we think that in this 1.6 billion kilometer, it is only the corner cases that actually contribute to the model's improvement. So now the idea is very simple. Can we extract these corner cases from this 1.6 billion kilometers? That's another story. But our focus is that how to utilize these 1.6 billion corner cases from the corner cases from this 1.6 billion kilometers. So based on the Tesla FSD data, it will gonna meet one corner cases in like 233 miles, which is like 300 kilometers here. So this is some kind of math. It doesn't matter. So that you want to sample one cases in roughly 300 kilometers in your 1.6 billion kilometers. And then based on the one sample of the corner cases, we could generate multiple future based on the work behavior work model and the MTGS to reconstruct the real world. And then it will roughly have 10 possible future based on these corner cases. So actually we are lowering down the 1.6 billion kilometers back into like 1 million kind of clips, with each clip like having 1 kilometers or no. So 1 million clips. This is not a very astonishing number to the industrial people. Industrial people collect nearly like 100 level, thousands level, even million level of clips based on all the data collection car running all over the world. So this is actually achievable. So this is not like 1.6 billion kilometers that is not achievable. And then I want to say that, okay, when we collect all these corner cases, how our end-to-end policy like to adjust them. Sorry, I might be running a bit of time. So I will go quick here. So actually we have a belief that when model has a bad cases or has a failure behavior, the most possible reason is that it has an outlier in this prediction. So what we want to do is that we want to eliminate such kind of outlier in the output distribution by lowering down the model's uncertainty about the scenario. So this is the core idea of Centra. We worked with NVIDIA recently to try to tackle down the corner cases in what we call the test time adaptation manner. And it actually reached the SOTA on the benchmark we proposed, the Nexus benchmark, and majorly improving in the time to collision cases where most collision cases happen before the collision. So like you're likely to have a very low time to collision score, then finally you're going to have a collision. And that's a takeaway of all today's work. We think that end-to-end driving will have made great efforts over the years, but what engine we propose here is the next generation to solve the corner cases in end-to-end driving. And how we achieve end-to-end driving, we first have a world model behavior world model to simulate the scenario, and then we have the Gaussian splatting method to reconstruct the scenario for the sensory input, and then we train the end-to-end policy through our RL method to have a better performance on the corner cases where we have lower uncertainties in the output distribution. And shout out to our team who contribute all this work together, and Hong Yang at Hong Kong University are also recruiting PhD, I postdoc, full-time employer all the way. Okay, and thank you all. I might take one or few questions because now next speaker will start soon here.
If you have a question, maybe you can come forward to the microphone.
Okay, maybe our next speaker.
Yes.
Can you see the schedule?
Yes. So is
Yeah.
Groove here.
Yeah, I think it's here.
So our next speaker for today is Groove Shah. Welcome, Groove.